This is going to be a recap of learning for lesson 2 from unit 3. And so we're going to be applying these 3 rules in order to identify what the domain is. Then we will graph it on a real number line, and then we will write it in interval notation. Let's get started. Let's look at example number 1. You were just watching if you were in front of me. So when I look at this, the very first thing I need to do is I need to glance and see that I don't see any radical. So I can eliminate the chance of it being rule 2 or rule 3 that needs to be applied. Then I look at rule 1. Rule 1 says if there's any type of variable in the denominator, I need to apply rule 1. So applying rule 1, I take x plus 2. It says it cannot equal 0. Algebraically, I solve. X cannot equal negative 2. I come off to the side. How do I represent this on the number line? It cannot equal negative 2, but it could be every other number. What does that even mean? That means that I could plug in any real number into this function, and it would correspond to an output value, except for negative 2. How do I write it as interval notation? Comes from the far left all the way to negative 2. We don't include it, and we go from negative 2 to positive infinity. We're looking at example number 2 right now. So g of x equals the square root of 3x minus 1. We're going to stop for just a second. I want to go over something you would have learned in Algebra 3-4. When you see this radical, if you see no little number hiding here, that's called the nth root, by the way. If you see no little number hiding there, it's a 2. So when I look up here, there's actually a hidden 2. Rule 2 and Rule 3 only apply when this nth root is even. It only applies when this nth root is even. So you're looking up here, you don't see an nth root, it's really a hidden 2. I'm seeing this radical in the numerator, and it again, the nth root is even, so I'm going to apply rule number 2. Rule number 2 says this quantity must be greater than or equal to 0. So I write that down algebraically, and then I'm going to go ahead and I'm going to solve for x, adding 1 to both sides. 3x is greater than or equal to 1 divided by 3. I have x is greater than or equal to 1/3. I come over to 1/3. This says I make a closed dot. This acts as long as the variable's on the left, like an arrow. I shade to the right. What does that mean? It means I could plug in any number, including 1/3 and to the right, into this function, and there would be a corresponding output value. How do I write that on a number line? We include 1/3, and it goes to the right. Looking at example number 3 right now. So how do I decide what rule, if any rules, applies? The first thing I do is I check, is there a radical? There is no radical, so I can eliminate the chance of applying rule 2 or 3, and then I look, is there any variables in the denominator? There is not, so rule 1, 2, or 3 does not apply. That means there's no limitation to what you plug in. You can plug in any real number, and you will get a corresponding real number back. So there is no limits. That stands for all real numbers, or you could write out the words all real numbers. How do we graph it? It's all the way across the number line, and we write it from negative infinity to positive infinity. So the first thing I'm doing is I'm deciding what rule applies. There is no radical, so I eliminate rule 2 or 3 from being applied, and then I look at rule 1. Is there any variable in the denominator? There is. So each of these denominators cannot equal 0 when we solve. Algebraically, I set them equal to 0, and then I solve. I'm adding 2 to both sides, so x cannot equal 2, and x cannot equal negative 1. We now need to represent it properly on a number line with the negative sign being to the left of the positive. It cannot equal these, so I circle them. It can be any other number but that. What does that mean? It means that if you took this equation and you plugged it into your calculator, you could plug in any real number except for these 2, and you'd get a corresponding output value. How do I write that? It comes from the far left all the way up to negative 1, but we don't include it, and it goes from negative 1 to 2, we don't include it, and it goes from 2 all the way to positive infinity. This is starting to get tricky. You're looking, you're like, oh, I see a radical, so it's either going to be rule 2 or rule 3. But this nth root is not even, it's a 3. It's called the cube root. That means rule 2 and rule 3 do not apply. And then for rule 1 to apply, we'd have to have a variable in the denominator, which we don't have. So rules 1, 2, or 3 don't apply. When that's the case, we are allowed to plug in any real number. How do we represent that? Negative infinity to positive infinity. Looking at our next example, so this would be example number 6. And so the first thing I'm looking at is I'm saying, okay, we do have a radical, but the radical Ooh, I think I tricked myself here. But the radical is a cube root, so I can't apply Rule 2 or Rule 3. I think I tricked myself. These rules are eliminated. But then I look at Rule 1, and Rule 1 says if there's any variable in the denominator, I have to apply Rule 1. So now I know that this portion cannot equal 0. So x plus 4 cannot equal 0. I'm subtracting 4 from both sides. X cannot equal negative 4. I come up to negative 4. It can be any other number except for negative 4. Just as a quick review, you can have 0 in the numerator, you just can never have the denominator. So if we plugged in a negative 4, negative 4 plus 4 is 0, the cube root of 0 is still 0, and we would be in trouble. How do I write this? Negative infinity all the way up to negative 4. We don't include it, and negative 4 to positive infinity. As a quick reminder for those that are watching this at home, whenever there is a denominator and it has a variable, we cannot ignore that. Rule 1 says we cannot ignore any denominator that has a variable. Okay, so I'm looking here, and I'm like, uh-oh, well, what's the nth root? When we don't see it, it's a hidden 2. So I'm going to apply rule number 2, which says that this has to be greater than or equal to 0. So greater than or equal to 0. We're going to apply what we learned in Unit 2, which was solving inequalities. So I'm going to come off to the side. What multiplies to give me positive 6 and combines to give me a negative 5, negative 2, and negative 3, x minus 2 and x minus 3. I'm going to set it equal to 0 while I try to find those hash marks, and I get 2 and I get 3. So here's 2 and here's 3. But again, remember when we learned this in Unit 2, it goes yes, no, yes, or vice versa, no, yes, no. How do I decide how I'm going to shade? I think as long as 0 is not a hash mark, it's easiest to test 0. So I'm testing this region right now. I'm plugging in 0. 0 squared is 0. Negative 5 times 0 is 0. Plus 6 is 6. So I have this statement. Is that a true or false statement? It's a true statement. I tested to the left of 2. It was true. So this is a yes, a no, and a yes. Also come back and look. This symbol says I need to have a closed dot. So this is what it looks like. How do I write that? Negative infinity all the way up to 2 we included, and we include 3 all the way to positive infinity. What does this even mean? It means I could plug in 5 to this equation and there'd be an output. I could plug in 10. I could plug in 0. I could plug in negative 10. I could not plug in 2.5 or 2.8 or 2.9. On example number 8, and students in front of me are trying to decide what example. So the thought process is, do we see any radical? No. So I eliminate 2 or 3 from being applied. The next one is I look straight at the denominator. If there's a variable in the denominator, I have to apply Rule 1. So I need to apply Rule 1 here. So I'm going to come off to the side. This says that x squared minus 6x plus 5 cannot equal 0. I'm going to go ahead and factor this. What multiplies to give us positive 5 and combines to give us negative 6? That'd be negative 2 and negative 3. So x minus 2 and x minus 3. Did we just do this problem? Or something similar? We did something similar, didn't we? Okay, that cannot equal 0, so this would be at 2 and this would be at 3. So, okay, hold on here. How about negative 5 and negative 1? Is that better? Thank you, Aubrey. So let's come back up here. Ooh, just pretend I didn't do that, guys. I can cut that out of the video. So x minus 5 and x minus 1. So I'm at 5 and I'm at 1. I need to put them in the right order. I'm at 1 and I'm at 5. It cannot equal 1 and 5. Why? Because if I plug in 1, I'd get 0 in the denominator. Can't have 0 in the denominator. You can have 0 in the numerator, but not the denominator. Cannot have 5. So it cannot be these things. They can be everything else. I'm going to give you right now 10 seconds to turn to your partner. How would I write this correctly in interval notation? Go. Now we're going to see problems in which more than one rule can be applied as we do the final 3 examples. So I do have a radical. The nth root is even. It's in the numerator, so I know that this portion has to be greater than or equal to 0. So x minus 10 must be greater than or equal to 0. Okay, good. Now I do have a variable in the denominator. I need to apply Rule 1. That means x minus 3 cannot equal 0. I'm going to come off now and do the work. Okay, so I add 10 to both sides. I get x is greater than or equal to 10. That's important. And I have that x cannot equal 3. So I'm going to start by using a pencil here. And I'm going to need a pencil in the final few examples. Okay, so I'm going to start by doing the first one. I'm going to go to positive 10. I make a closed dot, and we think of this as an arrow. I shade to the right. Then this says, hey, it just can't equal 3. That's all. So I'm going to see if you understand this. Could I plug in 20 into this equation and get an output? Yeah. Could I plug in 11? Yes. Could I plug in 10? Yes, I could plug in 10. Could I plug in 8? No. What about 2? No. What about 3? No. So when you see this number line, by the way, because 3 cannot be included, you may see a number line that just looks like this. They may not choose to actually put a circle there because it's not necessary, but this is correct as well as this. Let's look at our last 2 examples. Turn to your partner. What rule applies here? 1 and 2. Why? Because this is in fact even. So just like the last one, but this is a little more difficult, this portion must be greater than or equal to 0, and then this portion cannot equal 0. So I know x cannot equal negative 1. I'm going to apply that last just like I applied this last. Okay, so if we remember how we did this in Unit 2, we would set it equal to 0, and we're going to find those hash marks. Hopefully this time I do it right. What multiplies to give us 4 and combines to give us negative 5? Negative 4 and negative 1. So x minus 4 and x minus 1. I'm finding out those hash marks. So 4 is a hash mark and 1 is a hash mark. Okay, so 1 is a hash mark and 4 is a hash mark. Now if I look back up here, I can see I need to make a closed dot at those portions. I'm going to apply this later. Right now, all I'm going to do is I'm going to go back to Unit 2. It's going to be either yes, or vice versa, no, yes, no. It's going to alternate. How do I decide how it's going to alternate? Tell me what's the easiest number to test? 0. What's the only time we don't test 0? Yeah, if it's a hash mark. So I'm going to test 0 right now. So I'm going to plug it in here and test it. 0 squared, 0. Negative 5 times 0, 0. So 0, 0, 4. Is this a true statement or false statement? True. So I tested 0. This is a yes, this is a no, this is a yes. So I'm going to start by doing this. And now once I applied that numerator, now I'm going to apply the denominator. And the denominator says, hey, all that's good, but remember, x still can't equal negative 1. So I need to come over here. I need to identify approximately where negative 1 is, and I need to make a circle. So it's looking like this. On your paper right now, remember that's an open circle right there. On your paper, you have 10 seconds with the help of your partner. How would you write this correctly? The domain in interval notation. Ready? Get set and go. 10 seconds. You can write on the back of your paper. Always go from left to right. A common question I get is, Miss Bradley, does it really matter whether I use parentheses or brackets? It absolutely matters. It tells us whether we include a number as part of a domain. If we include in the domain, that means that number can be plugged in and we get a specific corresponding output value. I cannot include negative 1. I can include 1. I can include 4. Probably the trickiest problem is right here. Students in class are going on to the last example and seeing if they can achieve what is the domain, both visually on a number line, and then also after doing it algebraically, they're going to write it in interval notation. So what rules apply? So let's think about this. This is Rule 2, and so Rule 2 says that this portion must be greater than or equal to 0, and then this is Rule 3 because we have a radical with an nth root that's even in the denominator. That says that this portion must simply be greater than 0. So I'm going to do the algebra, I'm going to stop the kids in class, and then they're going to watch me graph it. So 4x is greater than or equal to 8. X is greater than or equal to 2. I'm going to apply that later. I'm going to factor this. What multiplies to negative 6 combines to negative 5. That's going to be negative 6 and positive 1. A lot of students forgot that they need to take this 2 and drop it underneath. So x minus 3, x plus 1/2. I'm finding those hash marks. So 3 and negative 1/2. How does this become tricky? We're going to start right now with understanding we have 2 different parts to this, and then we have to combine them to see where do things overlap. Are you ready? Let's start with this one. So I'm going to go to negative 1/2, approximated. Here's negative 1/2. And I'm going to go to positive 3. which is like somewhere over here. Okay? I can see that I'm working on the denominator. I can see that I have this symbol, which makes me believe I need to have an open circle. And now I need to decide, is it yes, no, yes, or vice versa, no, yes, no. Easiest number to plug in is 0. So I'm going to plug in 0 into this inequality. I have to have 0 squared times 2, that's 0. Negative 5 times 0, that's 0. So I have 0, 0, minus 3. So I'm looking at this statement. Is this a true statement? If people are confused, I took and I plugged 0 in here. So I'm testing this region right here. 0 squared is 0, times 2 is 0. Negative 5 times 0 is 0. So 0, 0, minus 3 is this statement. Is this statement true, yes or no? So this is a no, and this is a yes. So very, very lightly, do not use a pen. Very lightly, I'm going to shade this way and this way. Now I need to apply this statement up above, this statement. So I find where 2 is. 2 is about right here. I'm making a closed dot for 2, and I'm shading to the right. When you have multiple pieces to this, you have to apply both. So now think of double shading. Where's the only area where double shading occurs? Is there double shading over here? Nope, I'm not going to include it. Is there double shading at 2? There's only one shading right here. Where's the first place where I see double shading? It occurs here, but there's a problem. Does everybody see how there's an open circle down below? So if I'm going to put these together, it would look like this. I start at 3 with an open circle, and the only double shading is to the right. See the double shading? So this would be my final answer.